Hello everyone, and thank you for attending today's webinar, Smart Freezing for Plant-Based Foods, Why Choose Cryogenic Freezing for Plant-Based Products. Before we begin, we wanted to cover some basic housekeeping items. We will have a 40-minute session today, followed by 20 minutes of questions and answers. So if you have any question during the webcast, you can submit them already through the Q&A chat, and they will be resolved at the end of the session. If more detailed answer is needed or we run out of time, those questions that we didn't cover will be answered via email. And finally, an on-demand version of this webcast will be available approximately one day after the webcast, and it will be shared through a link with all the audience. In today's webinar, Anne Callens, Food Segment Manager of Products Europe, and John Tremblay, Technology Manager Cryogenic Applications at Products Europe, will present the plant-based event. That's everything on my side. We hope that you will enjoy the webcast. I pass it to you, Anne.
Yeah, thanks, Usui. Everybody hears me? Okay, so thanks for the introduction. And I will reverse the order of this webinar and start with some conclusions the attendees will make after this session. So, definitely, cryogenic freezing is a good choice for plant-based products. And why? Because of the optimal taste and texture, the long shelf life, the speed, the minimal space requirements, and the less food waste you have when you freeze cryogenically. So, but let's take a step back and ask ourselves, that moves, the slide did not move very well. So let's take a step back and ask ourselves the question, why the market is shifting to plant-based products? And the answer is very simple. You know, what we eat has become critical in how we combat climate crisis today. So on what we eat, we see that actually consumers are on board and they want healthier foods and for themselves and for the planet. More than 30% of the consumers would fully shift their diets to alternative proteins if doing so would have a major positive impact on climate. But there are still certain barriers to answer or to tackle for manufacturers. And let's say 4 of these barriers are listed here on the slide. It's really offering with plant-based products taste and texture that satisfies the consumers. Plant-based protein products sometimes still have a low nutritional value perception. How to tackle this? And then there is the cost of the product, premium products. And yeah, they are expensive. And we see that some of these product sales declines in the market. And then, you know, there still are elevated production costs. So what do processors need to do now to tackle this? One of the key things is the efficient product processing, going to lower costs. Secondly, it's keep the product taste and texture and the product quality, and therefore the importance of shelf life comes here on the table. Now, talking about shelf life, that means plant-based products need to be preserved as long as possible. And what is shelf life? It's stopping the growth of food poisoning microorganisms. It's slowing down the deterioration of nutrients. It's maintaining texture, taste, and aroma. And, you know, it's reducing the waste and increasing convenience. Oops. Okay, so food preservation takes a key role in the food supply chain, and it has an impact on the biggest impact on consumers' experience. Today, we're going to talk about 2 food preservation methods. We will talk about cryogenic freezing and modified atmosphere packaging. Food freezing and cryogenic freezing and modified atmosphere packaging are 2 technologies that exist amongst many others, but today really it's about freezing mainly. We have been doing a lot of work on modified atmosphere packaging as well with plant-based products. But John will rather take you here in the cryogenic freezing aspects of plant-based products and explain all the work we have done so far with plant-based products. So John, can I hand over to you now?
Yes, thank you. Good afternoon. Good afternoon, everybody. Hopefully you can hear me okay. So yes, I'm going to go through a little bit about the freezing, some of the trial work that we've done, and some of the fundamentals around why cryogenic freezing is the best solution, we believe, for plant-based products. So just very high level, what is freezing? Obviously, it's a process of which the water content of the food product becomes frozen, solid, or ice, and then the temperature is then further reduced down to the temperature required for storage, which is typically minus 18 degrees C for most products. And the advantages of freezing, just to build up on what Anne mentioned earlier, the minimal nutrition loss, retention of freshness, retain colors and flavors, no microbial contamination, and more importantly, no respiration or reduced respiration. And depending on the product, that can lead to quite significant shelf life improvements. So just a high level of what freezing is. What types of freezing are out there in the market? Typically, there's two types of main freezing methods. One is mechanical freezing and the other is cryogenic. So if I just talk about mechanical freezing, this typically involves a standard mechanical refrigeration cycle using a common refrigerant like ammonia or a closed loop carbon dioxide or a refrigerant equivalent. And mechanical freezing is most often used for high volume production of both raw and finished goods. There's various types of freezers associated with mechanical freezing, and they vary depending on the application, product conditions, quality, etc., to ensure the best quality. And it's often chosen, the freezing equipment normally is chosen to create the most efficient process needed for your product. And below is a list of some sort of typical examples of mechanical freezers: IQF freezers, which is individually quick frozen material, spiral freezers, tunnel freezers, plate freezers, and the other one I can't see because the slide thing is in the way, but anyway. Now, if I talk about cryogenic freezing, so this is a method that involves spraying or direct contact of a cryogenic material on top of the food, typically liquid nitrogen or liquid carbon dioxide. The product is frozen almost instantly while the refrigerant then is vented off to atmosphere. Cryogenic freezing equipment generally requires a lower upfront capital cost than mechanical freezing for the same capacity and requirements. And it's often used for products which are difficult to freeze or require individually quick frozen, individual samples like wings, etc. But lots of other bulk package items are also used where it's important to maintain them in individual pieces. It's also sometimes chosen where space is limited because you can obviously do a very large amount of refrigeration in a small footprint, which can mean lower cost in regard to the overall product cost, and also allows you to get into the marketplace very quickly. So just a very high level summary of what the two kind of freezing methods there are there, mechanical and cryogenic. Just move the slides on. Okay, so what actually is cryogenics? So cryogenics obviously is the science of very low temperatures, and for the sake of this topic, we're talking in the region below minus 78 degrees C, which is typically the temperature that CO2 sublimes, and you can see down here oxygen or nitrogen. It's got a boiling point of minus 195.8. So that's typically the region. We don't normally go into the super cold cryogenic area, but it's often good to define that range. Obviously, you can see on the scale here from water boiling right down to absolute zero. And on the right-hand side, there's a little photo of somebody using liquid nitrogen to give you a feel for what that product is. It's a cryogenic liquid, and yeah, so there's certain safety requirements that need to be considered when you're using. So in relation to the topic of today, what does controlled fast freezing actually mean? So a critical design parameter in any freezing process is the freezing rate itself. It's what we call the product freezing rate, which relates to the actual time that the product is actually frozen. And that is basically where, and the critical part of that is when the product changes state through the process. So the freezing rate is the rate of change in the temperature during the freezing process. It's normally defined as degrees C per hour, or in terms of depth penetration of the product centimeters per hour. And I'll talk a little bit about that later. And the most common physical changes that affect during freezing are, modification of the cell volume, dislocation of the water, mechanical damage, freeze cracking, freezer burn, and even ice recrystallization, all stages that can occur if you have different types of freezing rate and different kind of freezing conditions. On the right-hand side there, there's a nice photo of a strawberry which talks a little bit more about that. I'm not sure how clear that is to see in the webinar, but something you can look at later, but it shows sort of the different freezing rates and the different internal structural effects that can be caused according to those freezing rates. And so what do I mean by freezing rates, just to put that into some kind of dimension? So this in the chart here, we have slow freezing, controlled fast freezing. Typically slow freezing is an effect that occurs when you use a mechanical freezing process. So an air blast freezer or a spiral might give you a freezing rate of the sort of 0.2 to 0.5 centimeter per hour rate, and maybe contact plate freezers, etc., have a slightly higher rate of freezing, 0.5 to 3. And as you can see in a cryogenic freezer, where there's a picture in the bottom right hand corner there, that's controllable. So the heat transfer rate within the freezer can be adjusted according to the product. And typically the minimum can be anything from 10, but in certain conditions, you can get right up to 100 centimeters per hour. So a significant difference between the two technologies, or the two freezing processes. Let's move on to the next slide. So going back to what I mentioned earlier, so what does freezing rate and critical freezing time mean? In the chart on the left-hand side here, you can see some temperature refrigeration profiles for slow freezing, fast freezing, and what we call controlled fast freezing, as in the cryogenic zone. Excuse me. And the important thing to note is this critical freezing zone, where the product is actually freezing, typically around 0 degrees C, where the water would freeze. The time that the product is in that freezing zone has the impact on the final product quality. Typically, it's between 0 degrees and -5. We call the critical freezing zone. And that's where, as I said, most of the cellular freezing damage can occur. And just to give you some examples, at home, if you stick a bit of food in your freezer at home, that might take 19 hours or more to freeze. Mechanical freezer, you might be talking in 1 to 2 hours. Cryogenic freezer, you're talking in minutes. So the little green area you can see on the left-hand side. So the actual time within that critical freezing zone is minimized. Therefore, the benefit of the cellular structure is achieved. Some more sort of intermolecular pictures of what actually happens in the different freezing rates. On the top there, we've got the higher freezing rate, on the lower, the slower freezing rate. And this is something that's actually quite difficult to show in pictorial format, but these are some SEMs that we've generated for some earlier trials, and also from some published literature. You can see that the small fast freezing creates a very small amount of ice crystals. The cellular wall contact or structure is kept intact, so there's less damage when that product is thawed. Whereas in this slow freezing rate, there's a lot more ice growth, ice crystal size, even recrystallization of the ice through the process. That leads to fractures within the internal structure. More cellular damage leads to poorer texture, loss of nutrients, loss of pigments, color change, thawing. And the picture on the right-hand corner, again, it gives an idea of what those kind of structures can be within a product. And the top chart shows you a sort of top left, freezing speed, large ice crystals, faster speed, the smaller the ice crystal formation. So it just gives a sort of a picture or a representative of what can occur. So these are all things to consider in your freezing process. So what's the other impact of that associated with that? This is as freezing weight, well, actually weight loss that can occur during freezing. So during the freezing process, products can suffer or will suffer dehydration due to the surface conditions, and that dehydration can be significant depending on the type of freezing process used, even up to something like 10% in some cases. Cryogenic freezing generally has a significant impact on the reduction of dehydration because of the infinite freezing rate that you achieve and the rapid surface conditions compared to mechanical freezing, and the level of dehydration is typically is a lot lower and when the product is exposed to nitrogen, CO2, or very cold refrigerated air. Mechanical freezing has a different kind of heat transfer mechanism. It's more isothermal process, so there isn't a gradient in temperature during the cycle of the product, and that has a significant impact in the dehydration and the certain food starts. And that picture on the right hand side, I know it's not relative to plant-based, but it was the best picture I could find to show that this kind of effect of a thawed product, what can happen if it's frozen incorrectly. The thawing can lead to this leakage and this the liquid water that leaves the product as it goes through the process. So high cryogenic freezing rates equal low dehydration and weight loss. Now let's talk about some real life samples. So we've just completed an extensive analytical testing in our laboratory in the UK and in Barcelona in Spain on some soy-based burgers and at different types of freezing conditions. So on the left hand, well, both graphs have charts showing mechanical freezing and cryogenic freezing. Mechanical freezing is in the red line, cryogenic freezing is the blue line, and the control is just a normal product stored. So these are immediately frozen using liquid nitrogen freezer. You can see after day 0, the weight loss of the cryogenic is 0.16 compared with 0.53 for the mechanical freezing sample. And then if we look at the evolution over time, 2 days, 4 days, 6 days, 8 days, you can see the difference in the two. So for example, if we take 4 days, for example, we have a loss of about 2.5% versus 7.5% for a mechanical frozen product, and almost on the same line as a control product, which is a non-frozen product. And then if we look on the right-hand side, where we've done the same conditions, frozen cryogenically and then stored for a number of days at -18 degrees C, so stored for 15 days, and then looked at the evolution of moisture loss after thawing after those days. So day 15 was frozen, day 16, 17, 18, etc. up to day 24. And you can see, for example, say day 18, we're at a similar, so 3 days after thawing, similar weight loss condition compared with the control sample. But obviously the mechanical one you can see is growing and growing faster. So there. So just to summarize that, and I've written that in the bottom there to read, yeah. So this is weight loss evolution of soy-based burgers, yeah, just after freezing and stored in 4 degrees C for 7 days is the left-hand graph. The right-hand graph is right after freezing, then stored in a freezer for 18 days, then, sorry, -18 for 15 days, and then removed, placed in a normal fridge, and then taken out daily to measure the moisture loss. And you can see, and then I can summarize there, the difference between the two. 2.5% for day 4 in the case A versus 7.5 mechanical, and 2.5 versus 6.5 in the long-term storage trial. So just to reiterate what I've said earlier, you see the bigger the temperature difference between the refrigerant conditions, the faster the freezing time. So if you had air at -20 in a typical mechanical blast freezer, or CO2 in a CO2 freezer at -78, and then liquid nitrogen obviously at -1, -6, you have a huge temperature difference between the two, and therefore that affects in the freezing time. So for the soy-based burgers that I presented in the previous slides, typically we've seen freezing times of around 5 minutes for cryogenics versus 22 minutes for mechanical. So yeah, almost 75% less in freezing time. So in summary, yeah, what is controlled fast freezing again? So less tissue damage during freezing, improved yield quality in terms of flavor, texture, and appearance. And here is a couple of SEM photos that we took for the samples that we did in our lab tests, and to try and explain or show more clearly what we're saying. On the left-hand side, you can see the mechanical structure. On the right-hand side, the cryogenic structure. And then you can clearly see the difference between the ice formation within the product. So these are frozen samples that were then actually vacuum dried to remove the water, and then the dry product was then photographed or created the SEM image. So it's quite a nice way of seeing the structural differences between the two. And I think that concludes my summary on cryogenic freezing. So I'm going to hand it back to you, Asui, is it?
Yeah, thanks, John. So definitely with what you have been showing is that, cryogenic freezing of this soy burgers gave a product that was less damaged after freezing. There was, let's say, the texture. These same pictures that you were showing a much better texture for the cryogenic frozen products. And then secondary, the weight loss that you presented in your graphs for these soy burgers was also quite lower with this cryogenic frozen burgers. Just a quick question before I go in that bit here. So you have seen this for all your trials, for all the trials? Yeah, you have seen this. Yep.
Yeah, we've done, actually, that's just one example of one type of plant-based product that we tried. We've done other samples, and the trends are the same. Yeah.
Great. Okay. So in the beginning of the webinar, we were saying consumers are really choosing for plant-based products because they think they really are convinced that changing their diet, they will contribute to a better world. They will have less climate impact, and we have seen that using the right preservation method as cryogenic freezing, we can keep the texture of the products, the texture and the weight. So we are able to keep the food longer. So that would mean also, less food waste because the shelf life is longer. In the beginning of this webinar, I was also mentioning modified atmosphere packaging. We have some data on modified atmosphere packaging as well, but we won't talk about, let's say, the data we have got with these trials. That will be for a next webinar. But what I just wanted to show still today is the effect that modified atmosphere packaging has on food waste. And here in this graph, you see three things. You see on the left side products that have been packed with a graph that shows the CO2 emissions for products that have been packed with MAP. In the middle, there is air packed, and then at the right, there is over the counter. And really, what we see that MAP can extend shelf life by between 50 and 500%, depending on the product. And this enables really retail customers to manage their food purchases better and reduce food waste. So here in that example, you see food waste is less than 80% versus packaging in air. And it's less than 90% versus selling over the counter. The blue part of the chart is the impact of the food, and the green part is the impact of the plastic. So what shows here really with a packing food, a plant-based burger with MAP, you can really reduce the impact on the climate. So that was for MAP. The other example I wanted to present is about cryogenic freezing. And definitely cryogenic freezing contributes to less food waste as well. As John was explaining in his presentation, he was showing that with cryogenic freezing, you have less losses, less weight losses. You have seen there the picture with the meat. That was really a great example, John. So really, with cryogenic freezing, you can reduce the impact of food waste quite extensively as well. So here you see an example of a plant-based burger that has been frozen with cryogenics, and the other one mechanically, and the impact of the food waste with the cryogenic one is far lower. Voila, so that was it. I wanted to show you these examples, and I think, Usui, we are at the end of this session now.
Yeah, indeed. So thank you very much, Anna and John, for this talk and the great insights and the concept that you have been sharing with us today. And now it's time for some interesting questions, right? So please type all your questions in the Q&A section. Remember that those ones that are not covered, we will be responding by email. We'll let some time for the questions to come.
Okay, Usui, I see here the first question coming in.
Yep.
So someone is asking if the, let's say the work we did, we only showed soybean burgers. So if we worked with other plant-based protein products as well. So yes, we did. We did with different, we worked with different concentrations of soy, and then we worked on some pea products as well. So I hope that answers the question for the person who asked that question.
Yeah, in fact, Anne, just to jump in there, in
Yeah.
fact, yeah, we did, yeah, so far I think we've done four different types of food-based products, all slightly different in physical composition, etc. But yeah, to give us a broad range. But yeah, we just presented the soy-based stuff today because we didn't think we would have enough time to do all of them.
Okay.
Mm-hmm. Okay, I see another question. Someone is asking, are there also freezers for smaller production? So maybe we're thinking about the big, large production sizes, but the question is there something fitted for smaller productions?
Yes, yeah, I can answer that question, John, if you're okay. I answered that one. So definitely, in fact, the whole advantage of cryogenic freezing is that it's a very flexible system. So, for instance, you have the inline, let's say, systems where you talk about freezing tunnels, and you have all type of sizes that are available, longer and smaller ones. So that's one thing. Secondly, we also have, let's say, discontinuous systems. We call it batches. So it's a kind of a freezer cupboard, but it's a cryogenic freezing cabinet, and their products can be put on trolleys and frozen, let's say, yeah, frozen as well. And these are then smaller capacities, I would say, yeah, typically around, yeah, 120 kilograms you can put in one go.
Mm-hmm.
Hope that answered the question.
Another question actually related to cryogenic freezing. So here it says freezing with direct nitrogen doesn't burn the product, or you mix it with air to be around minus 80 degrees.
Yeah, I can answer that one. Good question. Yeah, well, yeah, whilst we are evaporating liquid nitrogen into the freezing process, yeah, it doesn't always, you know, it's not in direct contact with the cold liquid, so we normally evaporate it and create a very cold atmosphere. Some products can take that too, but the way in the freezing samples we did, we looked at different freezing conditions, hitting the product hard first with the contact of liquid, and then also other way would be to cool them gradually down and then hit them at the end. But you don't, yeah, if you get the control rate right, then there's no surface cracking or surface damage around the product. So it's exposed to a very cold environment, but by setting up your method of doing the control or your heat transfer rate on the product, then that would allow you to, you know, not cause that freezer burn activity. But you're right, if you just dropped a sample into pure liquid nitrogen, that would probably have some damaging effects on the product. So that's what we were saying in the slides earlier. It's about how you do that. Even though the rate of freezing is infinite, I would say you do it in a controlled way.
Mm-hmm.
Hopefully that answers the question.
Yeah, and maybe a question also related to what you just said, John. So you were saying that's the key of freezing on the controlled way, right? So the question is, can you use the same freezer for meat and plant-based product?
Yeah, it's the same. The freezing equipment is the same design, but the recipe or the profile that you would set up would be to suit the plant-based product. So yeah, so we have the flexibility that we can control the rate of freezing in different kind of conditions. As I said earlier, you can either have a fast rate at the beginning and a slower rate at the end, depending on the surface structure, or the other way around. So we have an adaptability within our cryogenic systems that allows us to be flexible. You compare that with a mechanical system, then it just goes in a one temperature. It's isothermal all the way through the process. There's no real controllability. It's just in there for a period of time. In a cryogenic freezer, it really is a controlled process from beginning to end. But yes, it can be. It's the same equipment. You wouldn't use the same equipment because of contamination, etc. But yes, it is essentially the same equipment, but repurposed with the recipes to suit the product that you want to freeze.
Mm-hmm. Okay. Another question, again coming to cryogenic freezing, of course, is what is the criteria of freezing with nitrogen or CO2? Why would you choose one or the other?
I leave it to you, John, to answer.
Well, it can be as simple as availability. Obviously, you can imagine CO2, there can be some availability challenges in the summer months, etc. But normally nitrogen gives you a more flexible rate. The cold energy that you can get from nitrogen, so evaporating liquid nitrogen and superheating the nitrogen, is generally 15 to 20% more than that with CO2. CO2 is more a snow effect, so you would use liquid CO2, you evaporate it, the snow comes in contact with the product, and that can have other conditions. So again, it depends on the product to be used, but normally from an economical perspective, the nitrogen is normally the better of the two. But it does depend on the product. If you're mixing products and you want the product to move with cold within it, then CO2 snow can be a good solution for that. So it really is process by process related. But if you're doing an inline tunnel freezing activity at reasonably high production rate, then nitrogen would always make more sense.
Mm-hmm. So you were mentioning really tailoring for process to process. So I have a question here. Is really that important to tailor freezer parameters for every single product, or can you use certain parameters which can adapt for a bunch of different products?
Yeah, I think the recipes that we could set up within our freezing process can be used for multiple products. You wouldn't actually have to have a specific one unless you had a very light product or a very easy damaged product. Then that might be something that was different, or you wanted to do chilling rather than freezing, or the inlet temperature is slightly different. There might be a slightly different recipe. But yeah, you wouldn't actually have to have an individual recipe for each product if it was very similar in inlet conditions and outlet conditions. If that makes sense.
Mm-hmm. Okay. I also see a question related to modified atmosphere packaging. Somebody is asking, why would I use MAP for packing my products instead of skin packaging?
Yeah, that's maybe one I could answer. Okay, so yeah, first of all, if you use skin packaging, the plastic is sticking to the product. So when you open the product, it gives a bit of that can impact the product itself. The other point is also with the MAP packaging. Recently, we have done quite some work with films that are biodegradable and recyclable, and we have got some good results. So the films you can use with MAP are really, let's say, I would say the packaging of the future, recyclable and biodegradable. And then another point as well regarding the shelf life, because we put, let's say, a gas mixture, we replace the air in the packaging with an adapted gas mixture, a mixture usually of CO2 and nitrogen, or it can even be oxygen. We really come to the optimal shelf life for the food product, while with skin packaging, you just remove the air. Okay.
Mm-hmm.
I hope that answers the question.
Yeah, thank you. Okay, back to freezing. Somebody's mentioning, I don't have the people neither the time to run this test on my facilities. How can I make sure I'm running my production correctly?
So can you just repeat that again? Oh, sorry, I don't have.
Yeah, so somebody's mentioning, I don't have the people neither the time to run this test on my facilities, the one that we have been talking about.
Yeah.
How can I make sure I'm running my production correctly?
Okay. Well, firstly, we would set up the process ourselves and do the validation ourselves to suit your requirements. Obviously, train your people, but also we can also remotely monitor the equipment to make sure that the process is retained at the right settings or the right parameters, or you're getting the right consistency of your product. So we could do that through our Freshline Smart technology platform, and we can monitor all the aspects of the freezer and provide daily reports, weekly reports, or even online dashboards that they can assess the data. So yeah, so we would do the initial setup ourselves first, do the commissioning of the plant, and then we would offer a monitoring service to make sure that the freezing conditions are maintained going forward.
Yeah.
That's for another webinar, maybe.
Yeah.
Indeed. Okay, thank you. I don't see any other question at the moment on the list, so I don't know if you, John and Anne, want to have some final remarks. We are really well in time, so we have time for some last conclusions.
For conclusion from my side is really that we see this space as really a growing space and let's say an opportunity to go to a more sustainable world. Cryogenic freezing and MAP are really two technologies that help to reduce food waste, and and in combination with plant-based, it's a perfect match. So that's one of my conclusion. And another conclusion I would like to say to all of you: we have the technologies in-house, we have the experts in-house. We are happy to test your products or to give you advice for any future development. John, anything from your side?
I think you've said everything very clearly there. As you say, we believe cryogenics has a fit in this space. It's an exciting new space, and we're more than happy to work with people to develop the right solutions for them. Yeah.
Definitely. Great.
Okay.
Thank you very much.
Thanks everybody for listening.
Thanks everyone for being here with us today. As I mentioned in the beginning, the session has been recorded, and we will share the link to watch it as many times as you want. Again, thanks everyone. Have a good day.
Thanks.
Thanks everybody. Bye. Are we free?